In the diagram here, you can see a simple circuit with a resistor, a battery, and a capacitor. When the capacitor is fully charged, it holds a positive charge on one plate and a negative charge on the other, indicated by plus Q and minus Q. The voltage across the capacitor reaches a maximum, and the current in the circuit stops flowing. This stored electric charge represents energy that can be released later when needed. This graph shows the relationship between potential difference, or voltage, and charge. As the charge increases, the voltage increases proportionally, which means it's a linear relationship. This helps us understand how energy storage devices like capacitors work, where charging the device stores energy by increasing the voltage across its plates directly in proportion to the amount of charge stored. The energy stored in a system can be understood by looking at the area under the line on a voltage versus charge graph. Here, voltage increases linearly with charge, forming a right triangle on the graph. The voltage is represented on the vertical axis, while the charge is on the horizontal axis. The work done in charging the capacitor corresponds to the area under this line on the voltage versus charge graph, which is the area of the triangle. This area is calculated as half the base times the height, giving us half of the total charge multiplied by the final voltage, or W equals 1/2 Q times V. This equation also represents the energy stored in the capacitor during the charging process. Recall that capacitance, C, is defined as the charge Q divided by the voltage V. By combining these two equations, we can also express the stored energy in different ways, like in terms of capacitance and voltage alone. We can make another useful equation by substituting voltage with charge divided by capacitance, which helps us connect the energy stored to the properties of the capacitor itself. This substitution simplifies the formula and guides us in calculating the energy based on the charge stored and the capacitor's capacitance. If you know how much charge the capacitor holds and its capacitance, you can find the energy it stores using this relationship. Next, we substitute the charge Q with the product of capacitance C and voltage V in the original formula. This substitution simplifies the expression for the work done to charge a capacitor, resulting in the equation W equals 1/2 times C times the square of V. A camera flash provides a quick burst of bright light that helps illuminate the subject, especially in low light conditions. This burst of light allows the camera to capture finer details and reduce shadows, resulting in clearer and sharper images. The energy comes from a capacitor, which can provide a quick burst of energy. Let's look at how uninterruptible power supplies, UPS, work when the main power goes out. The UPS draws energy from its capacitors or battery to keep the equipment running without any interruption. This backup power continues until the main power is restored, ensuring that critical systems stay online and avoid shutdowns or damage during outages. A defibrillator uses a high-voltage capacitor to store electrical energy, typically 100 to 360 joules, and release it rapidly, within milliseconds, through the patient's heart to correct arrhythmias.